Okay, hi everybody. We continue our discussion of rotational motion. And last time we considered such a problem when the axle of rotation was fixed in two roll bearings, and lead rod was fixed to the axis at some angle alpha, and two bodies of mass m at the ends, being at the ends of this rod, and all this structure rotated with angular velocity, so that each ball described a circle in such rotational motion. If we look upward at this structure, it rotates in this way, so that the vector of angular velocity is directed upward. And we established that the vector of angular momentum at any moment of time is perpendicular to this lead rod. And as the lead rod, as this massless rod rotates, vector L changes its direction. The end of vector L also rotates. If we look at this picture from upward, from this side, if we look from here, then that will be the axis of rotation O, and the end of vector L will describe a circle. It means that vector L is changing in time, not in magnitude, but in direction. And if at this moment of time we had such vector L, then at some next moment of time, vector L will be Lt plus dt, which is L of t plus dl. And the rate of change of angular momentum, according to laws of physics, which we have obtained, is determined by the vector of external torque of external forces acting on this system, on this rotating system. So if vector L is changing, dl is not equal to zero, then there is certainly some torque of external forces acting on this system. What should be this torque? By definition, it should be the sum of points of application of torque of forces, application of forces to different points of this body. So this sum will consist of two terms, R1 F1 plus R2 F2, two vector products, because we have only two bodies. The first vector is this one, R1, and the second vector is here. If this body M1, this is M2, if this body moves along some circular trajectory, what force should act on this body? Certainly a centripetal force, which is directed to the center of the circle. That will be force 1. And what force should act on the second body? Again, some centripetal force F2, which should be directed to the center of the circular trajectory. So we know everything in this equation. We know every term here. R1 being multiplied by vector F1. If this is a vector product, we have to rotate vector R1 to coincide with F1, and the direction of this rotation obviously will be towards the blackboard in this way, so that will be the direction of the torque of external force F1. On this picture, if we look from up downward, then this direction will be here, will be shown as perpendicular to vector L along the tangent line. So that will be the direction of vector M. So we have found the direction of the first term. If we consider the direction of the second term and multiply R2 by force F2, then you will see that the rotation is the same, and the direction will be the same from the audience to the blackboard. The vector product of R2 by force F2 will be directed to the blackboard. The same direction and the same vector here. So that will be the sum. That vector may be the sum of two terms. Both terms have the same direction. Where does this force come from? How does it appear? Who is acting? A force is a measure of interaction. What is another object with which this ball is interacting? There is no gravitational interaction, no electrostatic interaction, no magnetic interaction, no springs, nothing. Seems to be nothing like that. So where does this force appear from? And this force F2 also, how does it come here? It's obvious that according to Newton's third law, if any force is acting on this body, then some force should act on another body with which it's interacting, and another force should be directed. The force of action and reaction, and the force of reaction should be directed oppositely. It's obvious that if this construct consisting of the light rod and the axle of rotation, if this construct is rigid, then the force F1 occurs due to the reaction in the roll bearing. The roll bearing should act on the axle, and the axle should act on the roll bearing, and this force should be directed here. And at this roll bearing, the force should be directed here. So the torque is acting on the light rod from the axle, but opposite torque is acting from the rotating construction on the bearings. Another torque is acting on the bearings and on the machine which is holding all this construction. So that when the two light balls rotate at some angular velocity, there will be varying force, the force varying with time, acting on each bearing, on the upper bearing and on the lower bearing. This force will also rotate, and the bearing will be beaten some way. It will vibrate, and this vibration and this beating in the bearings is the real reason behind the torque of external forces, which cause this vector L change its direction. Now suppose that angle alpha, assume that angle alpha is 90 degrees. that is the right angle. In this case, the light rod will be perpendicular to the axis of rotation, and vector L will be directed along the axis of rotation, and the direction of vector L will coincide with the direction of omega. That will be the case of symmetry, symmetrical distribution of masses with respect to the axis of rotation. In this symmetrical case, vector L is directed along parallel to vector omega. And in this simple case of symmetrical distribution of masses, L will equal the moment of inertia and angular velocity. And moment of inertia, we know what is it. This is a scalar quantity. This is just a number which indicates the distribution of masses in some symmetrical body. This formula is convenient enough so that people wanted to keep this formula correct, even in the cases when vector L is not parallel to vector omega. Even in cases that we considered when vector L looks in some other direction. People wanted to retain this formula because it's very convenient. But what should be understood under this quantity moment of inertia if these two vectors are not parallel? They look in different directions. What should be I, moment of inertia? What quantity should act on the first vector in order to obtain some other vector directed differently? In general case, that should be a matrix. In general case. So that vector L has three components, Lx, Ly, and Lz. I will write these three components as the vector in such a column, a vertical column, and then matrix of moments of inertia will have this general form. This is a matrix, and so that could be written in such a form as which you must be well familiar with. And vector of omega also has its three components, which can be written in a column: omega x, omega y, and omega z. Are you familiar with such an expression? Have you learned it in linear algebra? I think you should have learned it in the first semester, right? So this is a matrix product of matrix multiplied by vector components, and as a result we obtain another vector which has different components, so that this vector described by these components does not coincide in direction with the second vector. This is a general way to describe this situation. So the main conclusion we have to make now is that in general case, when the mass of rotating body is distributed non-symmetrically with respect to the axis of rotation, in this general case, the moment of inertia of this body, of this rotating body, must be a matrix rather than a scalar quantity. It must have many components in order to ensure that the first vector and the second vector in this relationship, in this equality, do not coincide. The directions of these vectors do not coincide. So if any one of you If anyone has forgotten about this, or never learned and never seen this way of presenting matrices and matrix multiplication by vector, then please find it somewhere and learn this issue. This is very important in physics. Very important in physics, in different branches in different fields of physics. This is a mathematical field which is called linear algebra, which studies matrices, and please learn it and repeat this topic if you don't know it well, because it's very important. Now, this matrix is called tensor of inertia. And there is significant difference between simple matrix and a tensor. The tensor looks in the same way. It also has many components, like 9 components in this matrix. The tensor also has 9 components, and the tensor is also a matrix, always. But there is deep physical difference in physical meaning. The matrix is just a table of quantities. For example, a table of quantities. For example, this may be temperature in the morning, and this may be temperature of atmosphere at midday, and this is temperature at night, and this is humidity in the morning, humidity at daytime, and humidity at night. And this may be pressure of atmospheric pressure in the morning and at daytime, and pressure at night. This is a table of data, just a table. It will never change if you turn the system of coordinates, if you turn the reference frame. That table will remain the same. The temperatures will not change, which you have measured during the daytime. The pressures will not change. Everything will remain the same. This is just a table. That may be called a matrix. Matrix does not change when you turn the reference frame. But here, if you turn the reference frame, this matrix of the tensor of inertia will change, and will change in very particular way, because it's related to physical property of real body, of real object. And such mathematical objects which are related to properties of real objects, such mathematical objects are called tensors. So a tensor is a matrix, always, but a matrix is not always a tensor. That's it, the difference. So, in order to discuss the tensor of inertia, we must remember what is the angular momentum by definition. By definition, angular momentum I will put it here. Можно камеру повернуть? Товарищ, можно камеру повернуть? Не видно эту сторону доски. Okay, thank you. Да. So, the definition of angular momentum is what? That's a radius vector multiplied by momentum of a material point. So this is radius vector of some point mass. And this is momentum of this mass, which is mass times its velocity. So this formula is good for a point mass, the single point mass. It's not a whole rigid body. It's just one point. That will be mass times velocity. And the mass is constant and scalar quantity. It can be written first and then we have r times velocity, and then we recall what is velocity. That is omega angular velocity times radius vector. That is a kinematical formula which you must know well. We considered it in the first lecture. That's just a definition of angular momentum. And here we come to a double vector product. The double vector product is well known how you can transform it into a different way, into a more convenient way. If the first vector is A and the second vector is B and the third vector is C, then such a vector product is equal to B scalar product AC plus C scalar product AB. Also, certainly these are vectors. You may use vector notation here. But the important thing that this vector describes the direction of the first term, and this vector is responsible for the direction of the second term. And what is inside this round brackets is just a scalar product or dot product of two vectors. So this is a scalar quantity, and this is a scalar quantity. It's just a coefficient at vector C. So this is a mathematical formula. In English you say A, B, C, and so this formula will be read something like BAC minus CAB. In German it's ABC, and so this formula will be read like BATS minus ZAP, which is easier to remember, BATS minus ZAP. Okay, so if we use this formula, then the angular momentum can be written in the following way. That will be first vector B, that is omega, must be multiplied by scalar product of AC. AC will be R times R, which is R squared, plus the second term is vector C, which is R, minus, certainly, I told you correctly, but I wrote it incorrectly, minus here. Vector R times scalar product of AB, R omega, vector R omega. In such a form, this formula clearly indicates that vector of angular momentum L does not coincide in direction with the vector of angular velocity omega. If it were not for the second term, then the direction of omega would coincide with the direction of L. But the second term spoils this equation, and actually the direction of L will be the direction of omega with some coefficient R squared minus some other vector which has different direction. The direction of R, radius vector pointing to a mass point, does not coincide with the direction of omega. So in general case, the direction of this vector does not coincide with the direction of omega, which we discovered in our simple problem of two small balls on the light rod at angle alpha. And this formula can be used to find out, to derive all the elements of this matrix. And we will do this now. We will do this work. We will obtain the direct expressions for every element of this matrix. In order to obtain it, we must use the obvious expressions for vector quantity. Any vector quantity can be expressed through its components. So it's a unit vector I, Lx, x component of vector L, plus unit vector J, y component of vector L, plus unit vector K, z component of vector L. And vectors, unit vectors I, J, K look along the axis of Cartesian reference frame. So this is I, J, and K. These are the unit vectors of Cartesian reference frame. Also omega, vector omega can be expressed in the same way. That will be I omega x plus j omega y plus k omega z. And when we have such vector, such representation of vectors by components, we can easily calculate what is r squared, for example. Well, certainly vector r will be in this notation ix plus jy plus kz, vector kz. What is r squared, which is found here? R squared will be, according to Pythagorean theorem, x squared plus y squared plus z squared. Why do we know that? Because if we take this expression and multiply it by itself, then all the cross terms like I multiplied by j or I multiplied by k, all these such cross products will be zero because these unit vectors are perpendicular to one another. So their scalar product will give you zero, and only the first term multiplied by the second term, by the first term and the second element in this product will give you x squared, because I multiplied by I will give you unity. So that's r squared, which is found here. And what is the scalar product r times omega? Scalar product r omega, or dot product. We must multiply the second line and the third line here, and after such multiplication again, cross products will vanish because the unit vectors, different unit vectors, are perpendicular in Cartesian reference frame, and then such product will give you omega, x omega x plus y omega y plus z omega z. So if we know the components of all the vectors or coordinates of these vectors in a Cartesian reference frame, then we can easily calculate this coefficient and this coefficient. And then this formula will give you the following thing. That will give you m, I will continue here, m multiplied by vector I, or by vector omega, which is known to us, it's here, that is I omega x plus y omega y plus k omega z. And this vector omega should be multiplied by r squared, which we have already found, which is x squared plus y squared plus z squared, minus vector r, which is known to us. It's written here on the third line, which is ix plus jy plus kz, multiplied by scalar product r omega, which is also calculated here, which is x omega x plus y omega y plus z omega z. We close the square bracket and continue this equation here. We should not forget about this coefficient m, the mass of a point body. And then inside the square brackets, we will somehow open this round brackets and we will see what coefficient will be at unit vector I. At unit vector I, we will have omega x multiplied by x squared plus y squared plus z squared. And then we will have minus x multiplied by x omega x. So omega x here and omega x here will be the same, and x squared minus x squared will cancel. Okay, I will write it in greater detail. So I omega x will be multiplied by this round bracket x squared plus y squared plus z squared, and minus, now I'm interested only in coefficients at I omega x, I omega x, at coefficient at vector I. So that will be the first coefficient, and from the second term I will find it like I multiplied by x squared omega x, x squared omega x, plus x y omega y, plus x z omega z. Such will be the terms found with the unit vector I. With the unit vector I. X, y, omega y should be here. Yes, I have forgotten to put omega y here. And plus x z, x z omega z. That's it. And the round bracket should be closed. And similar terms may be found which accompany vector j and vector k. They will be something like very similar, with just we will discuss it later, with just a circular shift in indices. So if we look at this, I'm interested now only in a coefficient which is found at vector I. I consider only this coefficient, and this coefficient will be found like this, I, and if I open all the round brackets here, what is there? What is found there? Omega x, x squared minus omega x, x squared. So this term will cancel, it will disappear. And the only thing which will be here, which will remain here, that will be x omega x y squared plus z squared, because x squared was cancelled, minus x squared omega x cancelled, minus x y omega y minus x z omega z. That's it. If you remember about other terms, you will easily understand that other terms will have practically the same structure, the same logic, the same algebraic logic applies to all other terms which accompany other unit vectors. The same algebraic logic and the same structure, with the only difference that all the numbers x, y, and z will somehow substitute one another in this logic. X must be turned into y, and y will be turned into z, and z will be turned into x again. Such a circular change in indices. So if I know the expression, the first line expression, which is the coefficient at should be put in this way, the coefficient at vector I, then the same will be the coefficient at vector j, with the only difference that all the numbers should be circularly interchanged. We move it. Y will go into z, and z will be changed into x. Minus x will be changed into y, and y changed into z, and omega, instead of omega y, we obtain omega z, and minus y x, according to the same logic, omega x. That is I don't need this round bracket, I better put it like this way. Yes. And the last term here will be found in the same way, which will be vector k, and the same circular change of indices will give us z will go to x squared, x will go to y squared, y will go to z will go to change to x, omega x minus z y omega y. So, I worked. Oh, yes, you're right. Omega, yes, sure. Here will, I have forgotten it. Omega y, yes, thank you. And here is omega z. Yes, that's it. Omega should be at each term. Some component of omega x, omega y, omega z should be at every term here. Omega y, omega z, omega x. That's it. Now, after we have found this awkward expression, we know actually what? A coefficient found at unit vector I is what? If I was looking for components of vector L, and vector L can be expressed in this way, like vector I, some x component of vector x, vector j, y component of vector x, etc. So the coefficient which stands at vector I here is x component of vector L. So I know this x component. X component of vector L, I know it well, I have found it. That will be m omega x y squared plus z squared minus x y omega y minus x z omega z. That is x component. In the same way, I can write down y component and z component of this vector. In the same way. using this formula. Y component is the coefficient at j vector, and z component will be coefficient at k vector. Now, certainly there should be another round bracket like here, another round bracket, so that all this should be a coefficient at j vector and all this should be a coefficient at k vector. Certainly, yeah. I'm not attentive enough, not careful enough. Well, anyway, in this fashion we can obtain all the components of vector of angular momentum, x component, y component, and z component, expressed through the components of angular velocity, omega x, omega y, and omega z, and the components of radius vector r, which are just x, y, z, components, coordinates of our mass point, for which we want to find the angular momentum. And if you recall the matrix form, you will remember the matrix form which was written here using the laws of multiplication of matrix by a vector. You will understand that x component will be ixx times omega x plus another component of the tensor of inertia ixy times omega y plus another component ixz omega z. And comparing this expression with this expression for x component of vector L, we may immediately find the expression for xx component of the tensor of inertia will be a coefficient which is found here at omega x, which is m y squared plus z squared. And another component of the tensor of inertia will be another coefficient at omega y. That will be minus m x y. And the coefficient, the component of tensor of inertia yxz will be minus m. This m and this minus, I need to find the coefficient at omega z, that is xc. That is, I have found the first line of components of tensor of inertia, 3 components of tensor of inertia. Can you derive from here other components? Yes, certainly. I can immediately find component yy using this law of circular change of indices. So that will be m z squared plus x squared. And I can certainly find the component yzz, which will be m x squared plus y squared. And from here I can easily find component which is y, which is a component of the tensor of inertia with changed indices. From ixy, I can find the component iyx. I just change these indexes by. If I interchange these two components here, these two coefficients x and y, if I just change places, will anything change? No. I will obtain the same number. So iyx will equal to ixy. And also here, Ixz will be equal to Izx. So I have found how many elements of the tensor of inertia? 1, 2, 3, 4, 5, 6. How many are there? 9. You remember there are 9 components of tensor of inertia. Tensor of inertia is Ixx, Ixy, Ixz, Iyx, YY component, YZ component, and YZX, YZ, ZY, and ZZ component. That is the general expression for tensor of inertia. So I have found XX component, YY, and ZZ components. All the components which are found here at the main diagonal of this matrix. And also I have found X, Y component and YX component. They are equal. And also I have found X, Z component and ZX component. They are also equal. This is equal to this. Naturally, these remaining 2 components will be equal to one another also. These are also equal components. And it's not difficult to write down this component, YZ component. It can easily be found from the same principle that will be minus XY, XZ, YZ. That is, and that will be equal to IZ, Y component. So we have found all the components of this vector, of this tensor. What we have done, we have just considered an angular momentum of a single material point. But whenever we consider a solid body which consists of many material points, what do we have to do with this angular momentum, with this formula? We have to find angular momentum of each separate point, and then we have to sum all these angular momenta, so that we have to enumerate all the points in the solid body, the first point, the second, and so on, at point number k. So that will be angular momentum of point number k with its radius vector and with its mass k, and with its velocity k, and that will be the k index will be everywhere. That because that relates to a single point. Only omega will have no index, because omega is the angular velocity which is characteristic of the whole rigid body. It's the same for all the points. And we have even proven the theorem that omega does not change if we go to a different reference frame, moving reference frame. Omega is the same for all the points. So we must add index k to all these formulas, because that will be the coordinate of k's point number k, x, y, z coordinates of each point number k. And then, in order to find the total angular momentum, we will have to find the vector sum of angular momenta of all the points. And if we do this summation, then we will find the resulting tensor of inertia multiplied by the vector of omega, which is the same for all the points of solid body. But this summation will result in summing up all the components of the tensor of inertia. So actually we have to write down this is for a single point. If we need to find this component of tensor of inertia for the whole solid body, we must use the sum over all the points, and we must consider the coordinates of every point. And also here we must use the sum over all the points, and here and everywhere the sum over all the points, and here and everywhere. Okay, I will not waste my time. Everywhere there should be a summation. You will have to find the sum. In order to find each component of tensor of inertia, you must sum up these similar expressions over all the points of solid body. If the mass is distributed evenly, if this is some distribution in space, then each sum will turn into integral. You will have to integrate. And as there are two components, xy or xz, that will be a double integral over with two differentials dx, dy, dmx and dmy. So the final expressions for the components of the tensor of inertia of a rigid body, the final expression will be quite complicated if you turn it into an integral. I will write down just one component, x component. That will be an integral with respect to y and z components, So that will be an integral of y plus squared by c squared by dm, well, something like that. For each particular problem, that integral will take its own form, because dm will depend in different way over these components for each particular solid body. So each term, each element of the tensor of inertia will have quite a complicated form. I tell you the truth, that is the beginning of real mechanics. Real mechanics is not a second Newton's law. Second Newton's law is a primitive level, just for school children. Real mechanics starts in this way. When you go to tensor of inertia and integration over the whole volume of solid body, etc., etc. That's a real mechanic. And it's also appropriate to say that when you solve a problem, a real problem in real mechanics, you will, in general case, you will be unable to come to a solution, a final solution, without digital methods, without using computers and appropriate software and appropriate algorithms. Because real mechanical problems with real bodies will give you such complicated things, integrals and equations and differential equations, that it will be impossible to solve it in simple formulas just using a pencil and paper. You will need to use computer. And in order to find the most appropriate algorithms that work properly and efficiently, you must be able to transform all your equations and formulas into such a way which is most suitable for an appropriate algorithm and an appropriate software. So if you have a computer and software, it's absolutely not enough to solve the problem. What you must do first of all, you must write by hand all the formulas and transform all the expressions into such a way that is most suitable for your algorithm to be applied here. That's why physics is important. That if you don't know physics, you will be unable to use computers and software and applications, appropriate applications, because in order to use appropriate applications, you must first write down all the formulas and transform and necessary transformations to start using these formulas together with algorithms. So to solve every problem, you start from physics, always. First step, you must choose the appropriate laws of physics which apply to a particular problem. After you have chosen the appropriate laws, you must write down the formulas and apply these formulas to a particular problem. Take all the particular integrals which apply to your problem. And then after you have finished all this mathematics and physics together, then after that you may use appropriate applications and software, and your computer will give you some result. The result may be absolutely unreasonable and unrealistic if you make somewhere a mistake on this during these preliminary calculations and transformations. If you make a single mistake, no computer will ever give you a correct result. That's why in using such complicated formulas, you must always be able to check the correctness of your result. By yourself, no computer will ever check the correctness of your results for yourself instead of yourself. Only you can check the correctness. How to do it? First, we discussed it many times. First step to check the correctness of your results is to check the dimensions. The dimensions of quantities. The moment of inertia has the dimensions kilogram times meter squared. So each component of this tensor of inertia should have the same dimension, kilogram times meter squared. Is that correct here? Yes. The dimension is correct. That's the first indication that we made no mistake and missed nothing in this formula. And then, after checking the dimension, you must check for physical meaning, physical sense. The second step in checking the correctness of your results. If you don't check the correctness, you may overlook a mistake, and then no computer will ever help you to solve this problem. So that's as far as the tensor of inertia is concerned. Just a few final remarks. How many components are there in this tensor of inertia? Altogether 9 components, 3 times 3. 3 columns and 3 lines, 3 rows. Altogether 9 components. But these components, which are symmetric with respect to the main diagonal, these components are equal. And these two are equal, and these two are equal. So how many independent components are there in this tensor? 1, 2, 3, 4, 5, 6. Only 6 independent components. 6 independent components describe the inertial properties of any complicated solid body with respect to rotation. Rotational inertial properties. 6 components of tensor of inertia are enough to describe any solid body. But another thing which must be mentioned here, we have in our 3-dimensional space, we have 3 components of each vector, x, y, and z. So this is the dimension of this tensor is 3, but it has only 2 indices. Each component has 2 indices. Such tensors are called second-rank tensors. So 2 indices indicate that this tensor is of the second rank. So the tensor of the moment of inertia is the second-rank tensor. What is the first-rank tensor? You know well, the first-rank tensor is just an ordinary vector. It has only one. It has only a single index. When you present this vector through its components in Cartesian system, it has only one index, x, y, z. So this is a one-rank tensor, first-rank tensor. First-rank tensor is a simple vector. And what is a zero-rank tensor? Zero rank tensor is a scalar, just a number, just a quantity. Scalar quantity is a zero rank tensor. And first rank tensor is a vector, which is just one column in this matrix. And second rank tensor is 9 quantities. For symmetric tensors, 6 of them are independent. And other tensors of rank 3, third rank tensor, certainly, and fourth rank tensor, certainly. There are, in some fields of physics, there are more complicated tensors which have a higher rank, third rank and fourth rank tensors, yes, in some fields of physics. So you must be aware of this mathematical tool, which is called a tensor algebra. You must be aware of it, and you must be ready to use it in different fields of physics. And you must know what is the rank of tensor. The rank is the number of indices. If you have 2 indices here, and the tensor is expressed then through such matrix, then this is a second rank tensor. What is particularly about tensor is that its components are expressed through the coordinates of radius vector. But when the solid body rotates, the coordinates of each point change in time, because the point goes along some trajectory, circular trajectory. So each point is a function of time. Xk is a function of time. And y component of point number k is also some function of time. And z component of point number k is also a function of time. And when you substitute all these functions of time into these integrals, you will obtain that each element of the tensor of inertia is a function of time. It's not constant, it's changing. As the body rotates, all the components change. That's obvious, because these are coordinates of point number k, and point number k goes along the circular trajectory, so all its coordinates are functions of time. So this is quite a complicated object. It has 9 components, 6 of them are independent, and each component is a function of time. That's it. And in order to calculate each component, you must, in general case, take some integral over the whole volume of a solid body. That's it. That's as far as the tensor of inertia is concerned. Now, I wanted to consider a simple problem. Soon we will conclude our consideration of rotational motion. Soon we will come to the end and finish with rotation. But before we finish with it, we must discuss the solution of some particular problems. By the way, soon you will have a mid-semester written test. I wanted to ask you which date or which day of the week is most suitable for you. I looked into your schedule of your classes. It seems to me that Saturday is the best day to take the written test. The written test will have 3-hour duration. It will be given during 3 hours. So I suggest that you have a written test from 3 p.m. until 6 p.m. on Saturday. But it will be not this Saturday on this week, but the next week. Next week Saturday from 3 to 6. Is that okay with you? So let's fix it at this the written test will be on Saturday next week from 3 to 6. Next week, Saturday. That's about 10 days from now. Also, during this week, you have to finish all the problems related to the first assignment. Some of you have already done with the first assignment, but not all of you, not all of the students. So you must finish all the problems of the first assignment, and then you will have a week to prepare for the written test. That is a week to repeat all the laws of physics and the solutions, ways of solutions of problems in order to get prepared for the written test. So 1 week will be just for preparation for the written test without any solutions, regular solutions of your home assignment number 2. Home assignment number 2 will start after the written test. Also, after the written test, we will arrange for the defense of your home assignment number 1. We will arrange for another date for it. Now we have some time, and I will discuss the solution of one problem. Suppose we have a uniform rod of length L and mass M, and the rod is on the surface of horizontal surface of the table. So this is a surface of the table, and you look at on the surface of the table. And the surface is smooth so that there is no friction. This rod may move without friction along the surface of the table. And there is a body which moves on the surface of the table. The body has the same mass as the mass of the rod, and it has some velocity. And the body strikes at the end of the rod and sticks to the rod. So this is an absolutely inelastic collision, absolutely inelastic impact. All this happens without friction. The question is, what will be the velocity of point A immediately after the collision? What will be the velocity of point A of the rod immediately after the collision? The velocity in magnitude and in direction. So you have to calculate whether this point will move in this direction or in opposite direction immediately after the collision. I may give you a hint that this point will move in opposite direction just a moment after the collision. And certainly this point, this end of the rod, will move in the same direction. And there will be some point on the rod which will remain at rest during the first short period of time after the collision. And that will be the instant axis of rotation, which is at rest with respect to our reference frame, laboratory reference frame, from where we observe this phenomenon. So this is just a hint, but you have to prove all this, what happens here. Which laws of physics should be applied in this problem? First law of physics is the law of motion of the center of inertia of the system of bodies. So these two bodies, the rod with uniformly distributed mass, and the body, the small body, which moves here. This is the closed system because no other forces act on it. Certainly there is a force of gravity which is perpendicular to the table surface and the force of reaction from the table surface, but these two forces cancel each other. We don't have to take them into account. So this is a closed system, no other forces act on it, and therefore, if no other forces act on it, then the second Newton's law applied to the center of mass of the system of bodies. The second Newton's law, we derived it for the center of mass for the momentum of the center of mass. And from this law we obtain here that if this is a closed system, then the force is zero. That is the total external force, that is zero, and therefore the momentum of the center of mass is constant. That's the first law of physics which can be applied here. Where is the center of mass of the rod? As the mass is uniformly distributed, the center of mass is at the center of this rod. So where is the center of mass of the whole system? At this moment of time shown in this picture, the center of mass should be somewhere on the line connecting these 2 points, and as the masses are equal, the center of mass will belong to the center of this section. In some moment of time when this body will move here, the center of mass will be at the center of this section, and then it will be at this point. And then when the body sticks to the rod, the center of mass will be here. So the center of mass moves along this trajectory, and it will continue its motion along the same line, because according to the law of conservation of momentum, this is the law of conservation of momentum, the total momentum, the total velocity of the center of mass of the system, closed system of bodies, is constant. It will remain the same as it was before the impact. It will remain after the impact, after the collision. It will be the same as before. And what was the velocity of the center of mass before the collision? It was v over 2. Obviously, it will remain v over 2 here. So after the collision, this point of the rod will continue motion, will start motion along the same line as the center of motion to which the center of mass belonged before the collision. And this point of the rod will move in this direction along the same line with velocity v over 2, half the initial velocity. That's the law of conservation of momentum for a closed system of bodies. Now, in order to find the velocity of point A, we need to find the angular velocity of rotation of this rod. Certainly it will rotate because something pushed it here at this end, and it was lying on the table at rest, and after this push, the rod will start rotating. How to find the angular velocity of rotation? We must use the law of conservation of angular momentum. Because there are no external forces acting on this system, therefore the total torque of external forces, the total torque is zero. And therefore the angular momentum, the total angular momentum, is also conserved. It's constant. And in the beginning, before the collision, what was the angular momentum with respect to the center of mass of the total system? What was the angular momentum just before the collision with respect to this point, the center of mass of the total system of bodies? What was the angular momentum? Well, it was the r, which is L over 4, just 1/4 of the whole length, multiplied by the momentum of this body mv, by definition of angular momentum. That was the angular momentum before the collision, and it will remain the same. But after the collision, this angular momentum will be expressed like, this is the vector, will be expressed like the total moment of inertia times angular momentum, and that will be the total moment of inertia with respect to the center of mass of the system of bodies. That is, with respect to this point. Center of mass, let's let it be this way. This is the center C of the rod, and this is the center of mass of the total system of bodies. And that should be equal the moment the angular momentum just before the collision, Lmv over 4. What do we know here in this formula? Do we know the moment of inertia? Certainly, yes, we do. We can calculate the moment of inertia of the total system with respect to the center of mass. Can we do it? Yes, because we know the moment of inertia of the rod with respect to point C. That is 1 over 12mL squared. We derived this formula, the moment of inertia of a uniform rod of length L and mass m with respect to its center, the center of the rod. And the moment of inertia with respect to the center of mass of the system will be found due to Steiner's theorem, which is the moment of inertia with respect to the center of mass of the rod plus ma squared. ma, and a is L over 4 squared. So can we calculate it? Yes, certainly we can. That will be ml squared, and here we'll have 1 over 12 plus 1 over 12 plus 1 over 16. Yes, we can do it, no problem. So we know this. I will not waste my time because we have just a minute before the bell. We know this moment of inertia. You can easily calculate it. We know this quantity, and if we know this quantity, we can calculate omega. Yes, we can do it now. We can find it. And if we know omega, we can immediately find the velocity of point A. What will be the velocity of point A? That will be the velocity of just after the impact, the velocity of point of the center of mass plus omega, distance to point L, which is 3L over 4. That's it. We can find it. We can substitute to the velocity of the center of mass v over 2. And here we will substitute omega, calculated from these simple equations. You know omega from this equation, and that's very simple. You will find VA. But you must take into account that V center of mass is directed to the right, but the omega is the angular velocity of rotation, which will be obviously, the rod will rotate obviously counterclockwise. So actually there must be minus sign here, because the velocity of point A due to rotation is directed oppositely the velocity of the center of mass, opposite to the velocity of the center of mass. If this velocity of the center of mass v over 2 is positive, if we assume that this is positive direction for velocities, then the velocity due to rotation of point A will be negative. And when you substitute all the found values here, you will discover that the second term is larger than the first term, and actually the velocity of point A at the first moment after the impact will be directed in the opposite direction. Will have opposite direction to the initial velocity of the body. And knowing the velocity of this point and this point, you will easily find the position of the point which will remain at rest. That is the distance A. You can easily find this quantity Please do this at home. Similar problems will be offered to you both during the written test and written exam in physics and oral exam in physics. Similar problems with similar way of reasoning will be offered to you. So please finish this problem and find which point will remain at rest after the collision, immediately after the collision, and what will be the velocity of point A, and why the velocity is directed here to the left. Well, you must be able to explain it based on the laws of physics. Okay, let it be the end of this lecture. Next time I will show you some very interesting experimental demonstrations in our demonstrational cabinet. During the lecture we will observe gyroscopes and the motion of gyroscopes and the precession of gyroscope and the nutation of gyroscope, all the interesting phenomena related to the motion of gyroscopes. So that will be next time. And now let's finish this.